Assalamu alaikum wa rahmatullahi wa barakatuh. Today we'll be talking about the sixth chapter in the HVAC specialist course of KNX. This chapter is called about steering and adjustment. And the concept is very simple, so let's start ahead. Two examples here. When you are dialing on a radio that allows you to adjust the volume, it's often used as volume controlling. In this way, as based on the book, you are steering, okay, not adjustment, because it's only up and down. Then talking about driving a car. In driving a car, you have to adjust based on the environment around you. So it's called adjusted. Okay. However, let's talk about this in a more of HVAC word to get you the idea. Because what you will find out eventually that adjusting is what we are doing in our normal daily life. It's not steering. Steering is one way direction without getting feedback, without adjusting our way depending on the external environment. But adjusting is the way that most of our life is depending on. So let's talk it in the HVAC way. So based on KNX association, they are trying to tell us how steering works. A room is heated by radiators, okay, normal. So you adjusted the radiator in your room, let's say to 22%. By selecting setting on a radiator valve, a specific amount of heat is released into a room. So now the room, the flow temperature is 22 centigrade, okay? 20 Celsius, okay? Then something happened. They have an external environment, like the sun came, okay? So the room is heated by a radiator for 22, but then the sun came. Then normally now you have the flow coming from the radiator plus the flow coming from the sun. And let's say now the room is not 22 anymore. The room temperature is now 25 because the flow temperature coming from the radiator is fixed. And then you added the sun radiation on it, then the temperature overall now is 25 C. Okay, so this is the steering. Now let's say it came in the evening, okay? Still I'm trying, my radiation or my radiator is pushing for 22, but now the sun goes away, then it's a little bit cold, it's a little bit cloudy, then the outside temperature is less, then this is taking away from the 22 I have. Now the eventual temperature, if I measure it now, is only 17 because the external temperature is colder now. So the temperature, overall temperature now is 17, not 22. However, in the beginning, I wanted to have it 22. The idea here that I did not adjust my temperature based on the external factors. So I did not react to the external factors, okay? This is why they call it steering. Steering meaning what? I did not get any feedback. So to explain it more, steering is disruptions are not offset, meaning that any external factor to my calculation, I did not try to countermeasure. So the key characteristic of steering is the lack of feedback between the output value, in our case is temperature, pressure, maybe voltage, and the control variable, input value standard. This is known as an open process. So the steering is based on an open process where disruptions alter the output value until they are resolved. Okay, the flow temperature remains constant. This is the steering. Let's get another way. So block diagram of a steering in a very simple way. I have a command device person. This, let's say myself. I get an input value. Okay, the input value starts putting control variable, and then the valve is open to specific value. Then the disruption comes, like the sun, like the wind, like the cloud, like the external temperature, but there is no feedback. So my value is not changed. So whatever input or command I made is not getting a feedback from the external. This is why it's a steering. So it's one direction I'm going to. Let's talk about the same example, but in an adjustment. So the same example, okay. I open the valve to give me a 22 degree in my room. Then the sun came. When the sun came in the other example, I did not consider the sun in my example, so it reached 25 C. In this way, no, the room is heated by radiator. The radiator valves are thermostats. Thermostats meaning that they also can work with the feedback coming from external sources. So the control or input variable, valve position is 3. The sun supplies energy to the room. The thermostatic valve registers this and reduces the energy supply to the radiator. So it's starting to lower the temperature getting from the radiator by around the 3 C. to make sure that the temperature in the room is always 22 C. Okay, so the flow temperature remains constant. The water volume is lower to decrease the water supply or the temperature from the radiator by the 3C to make sure that the sun effect is calculated and adjusted. Okay, same thing in the external when it's colder. So the same example, but now I have to get more water, so the water volume is greater because now the thermostat find out that the temperature is getting colder, so I need to have more water volume to make it also now more hot, to make sure that in the room is always 22 C. So this is the idea of the adjustment. So the adjustment, I am taking the disruptions in my consideration and offsetting them. So the key characteristic on control is the existence of feedback between the output value, temperature, and the control variable input. They are constantly compared against one another. This is described as a closed loop. So the steering was an open loop. This one is a closed loop. Disruptions have no or only very little effect on the output value. So they're not really affecting the room temperature because I'm offsetting them. My thermostat and my system is an adjusting system and working as a closed loop and adjusting that. Okay, so the flow temperature remains constant. Okay, this is the main difference between adjusting and steering. So in this way, adjustment set point actual value. And you will know this in the next chapter when we talk about the room temperature and how to control it. You found that the thermostat in your room temperature is always calculating the difference between the actual temperature that you have now and the set point temperature or the temperature that you want to reach. And this difference is controlling the valve of the flow of the temperature or the flow of the water affecting the temperature or the heating or the cooling in the surrounding area around me in my room as an example. So here you have a command device. I have a set point temperature or value which I want to reach. Okay, and then I have a comparator here, something to compare. It's comparing the actual value that I have now and the temperature that I want to reach. Okay, I'm getting a value. This value is going to the controller to affect how the controller will work. Okay, as long as the actual value matches the set point value, the comparator finds no control deviation. So if they are the same, so I don't have to do anything, thus the control deviation is 0. The controller generates a control variable that leaves the actuator in its current position. So I'm not changing the current position. Okay. However, if the set point value is higher than the actual value, okay, the comparator produces a positive output signal. The controller then generates a control variable that further opens the actuator. A large quantity of hot water flows through the radiator per unit of time. So in this way, I want more heat. So the set point value I need is more than the actual value. So simply I'm sending it to my system to get me more water because I need more heat in my room. Okay, and then it can also work vice versa. In this case, if the set point value is lower, so I don't want more heat, I need less heat. The control set point value is lower than the actual value. The comparator, okay, produce a negative output signal. The controller must then generate a control variable that further closes the actuator. A smaller amount of hot water flows. So normally, in a very simple way, the comparator is responsible to find out where the deviation, sending it to the controller, which depending on the value coming from the comparator will affect your actuator. Your actuator might be a fan coil unit, maybe a valve to control the heat, to raise the heat or lower the heat demanded. Okay, so this is the closed loop. Okay, and the actuator here should be able to sense and to respond to this temperature changes. So the controller influences the actuator with the control variable. Actuators can either be adjusted continuously or incrementally between two end positions, on and off. In the simplest case, the actual job is to dispense a mass of energy flows. Some of the actuators are only using on off. Some actuators are using valve where you can change how much the valve is open depending on the actuator itself. Energy flows can consist of gas, steam, oil, water. Energy flows are mostly electricity. The mass or energy flows are often the actual value or influence it in the heating or energy consumption. Okay, this one is continually adjustable. This one is only on and off, depending on the valve that you have and the actuator that you have. Now we're talking about a sensor in the actuator itself, because you need a sensor to tell you the feedback, and then getting the feedback here in the controller itself as part of the comparator. So the comparator can only compare, okay, the set point value and the actual value if both are the same physical variable. Of course, it will compare temperature, and compare voltage to voltage. So it should be the same physical variable. For example, if set point value is specified as an electrical voltage, the actual value must be also an electrical voltage for the comparator to work. So the comparator is the one making the comparison, giving the value to the controller. Okay. Sensors here, as you can see, are affecting and responsible to make this value of the temperature, converting it to electrical voltage. So the sensor converts temperature into electrical current. Okay, actual value of control variable converted into electrical voltage as well. Okay, probes or sensors convert the actual value into the required signal. Closed loop and a summary steering open sequence. Okay, with no adjustment to closed sequence. In an adjustment control system, a comparator is always checking that the set point and actual values match. Disturbance change the actual value. True. If the comparator recognizes the difference between the set point and the actual value, it transmits control deviation to the controller. The controller's job is to ensure the actual value always matches the set point value. So the controller is closing the valve and open it, okay, as many times as needed to make sure that the differentiation or the deviation between the actual value and set point value is so small, hopefully the same one. Okay, the controller influences the control path and not the actual value with the actuator. Closed loops are everywhere, and this is our life. We are always adjusting to what's happening around us. So here is saying that control is not just a technical term, it's used in many other contexts. So closed loops are the human body, maintaining about temperature of 37 C, ensuring the energy supply, food, water balance. So when you are hungry, you eat. We are adjusting, okay? You are feeling hydrated, you drink more water, okay? When you are feeling cold, you get more coverage. Okay, walking upright, very demanding control. Okay, this is how our life is. Adjustment when driving, respectively, safely distance of car. We are doing it everywhere, doing driving, doing biology everywhere. This is the closed system. Okay, interpersonal relationships also is a closed system where you adjust with the other people around you. Even in society, it's the same. So democracy also has its own closed loops. The difference between the popular will, the set point, and the dominant policy, the election, the actual value is determined cyclically in elections. Okay. Okay. So the idea that closed loops everywhere, different closed loops comes in many shapes and forms, based on whether the actuator can only switch on and off. Okay. Or whether it can be set to any position from 0% to 100%. As I told you, actuators can come as on and off. So closing a valve or opening a valve, that's it. Or a valve that be controlled for different areas and different opening from 0% to 100%. Okay, how accurate the set point must be maintained, how quickly the system must react. All of these are affecting the system that you have. The accuracy of the system, the fast, let's say, reaction of the system, whether to and what extent any overshoot can be tolerated after disturbance or set point changes, whether the system tends to fluctuate, containers unloading crane or not. Sometimes systems fluctuation, I told you. So normally you have a very small gap where the system shouldn't increase the art of control technology consists of selecting the appropriate controller for each control path and each control task and calibrating it appropriately. This is the way that where real adjustment system works. Then it's talking about the switching controller types. You have 2-point controllers. Okay, actual set point turn on, which is a turn on and turn off only. Okay, the good thing about it, simple design, faster action, but the accuracy is low. Okay, then you have a 3-point controllers. Okay, if actual set point lower limit heat or cool, so you have 3 points. So it's on to heat or on to cool or off totally. Okay, this still simple design, fast reaction, better control accuracy than the 2 points. Okay, but still energy consumption is very high and the risk of energy waste, heating and cooling in alternation if not configured correctly. Okay, this like what? Like a simple room temperature control. Different ways is the P or I or D. Okay, sometimes you have a PID controller where it can have better deviation, alternation, and much quicker response. So the P1 is the greater the deviation, the greater the control variable. Immediate reaction, permanent control deviation. It's used in water level control in toilets. Okay, the lower the water level, the wider the inlet valve opens. Another one is the integral controller, which is the I, reacts to long-term effects. Okay, then you have a D controller, differentiation controller, reacts to jolts, short-term effects. All of this have a lot of equations. We're not responsible to know them, but you need to know that they are different types. So you have the on-off, the 3-point, and the PID controllers, PI or PD or PID controllers, which the controller composed of the basic component from PI and D controllers combined for a common control variable. KNX room temperature, use the PID in most of the time. Okay. KNX room temperature control either with switching 2 or 3-point controllers, or in higher quality systems with the continuous PI controllers, a combination of P and I controllers. Okay, this is what we use in our KNX normally. Okay, this is what we had in this course, in this chapter. Next chapter, we'll talk about the individual room temperature control, which is the component of the KNX that will be used in our system. Okay, see you inshallah next chapter. If you have any question, let me know, and see you in the next chapter inshallah. Salam.